Hello everybody. So in the last video we saw what is sampling distribution of mean. So in this video we would like to see what will be the distribution of the sampling distribution of mean if the original population is normally distributed, right? So this is an important result. This will this is the foundation for your hypothesis testing, finding the confidence intervals and all those things, right? So let us see what let us start from where we left in the last video. We said that we have a sample size of 30, right? We are asking 30 people randomly selected that what's their height in the age group of 30 to 35, and then we repeated the experiment, say 10,000 times. Yes, 10,000 times we repeated the experiment, right? So what will happen? If I ask the first group of 30 people, they are randomly selected people, I will ask their heights. They will tell me some numbers. So let me denote those numbers as x1, then x2, then x3, and so on, x30. And because this is the first set of people I'm asking, so I'm just putting 1 on the top. And then I'll go to the second group of people. Again, they are randomly selected. So I'll call them as x1, x2, x3, x30. And I put a superscript of 2 because this is the second group of people I'm asking. And then the 10,000 group. So I call the numbers as x1, x2, x3 and x30. And because of the same reason, I'll put the superscript as 10,000. So now you see this is the data I am having, right? So when you study in books, the things are abstract, but I just want to give you a feeling like what exactly we are doing. You actually don't need to deal with these data sets, but I just want to tell you that what exactly your x1 is and x2 is. Now you look at this first column. What is this? This is a random variable, right? This is a random variable. Let us call this random variable as x1. Okay, because these are the realizations of a random variable x1. And then what is the second thing? Second column again is realization of random variable. Call it as x2 and so on. Call the third one as x3 and so on. And the fourth one as so the 30th one as x30. So you see x1, x2, x3, x30. These are your random numbers. And what will be your x bar? X bar will be nothing but, okay, so x1 x bar will be nothing but x1 plus x2 plus so on x30 divided by 30. Because you see how you were calculating the averages. So you were if you calculate the average here, add these numbers, okay, add these numbers, and then you add these numbers by 30, add these numbers by 30. That is same as one realization of x1 and then one realization of x2 and one realization of x3 divided by 30. So x bar is a random variable. So what I am doing is, if I do these things, x bar, if I do here, let me add another column. If I add x1 plus x2 plus so on x30 divided by 30, I'll get another column which will be nothing but summation xi1 divided by 30. Here I'll get summation xi2 divided by 30. Here I'll get summation xi 10,000 divided by 30. So that's what we were talking about in the last video, right? Okay, great. So now what we are saying, now if your original population is normally distributed, so that means this x1, which is just the numbers you have taken from that population only, so x1 is also normally distributed with the same mu and same variance or standard deviation, right? Suppose your original population is normally distributed with mean mu and standard deviation sigma square or variance sigma square. So x2 will also be, x2 is also from the same population, so x2 is also normally distributed, right? And so on. And x30 is also normally distributed, right? Now let us look at x bar. Then x bar is x1 plus x2 plus x30 know that all of them are random variables, right? Now if I look at the expected value of x bar, that would be expected value of x1 plus x2 plus so on x30 divided by 30. So you use your results of expectations results. So 1 by 30 constant will come out. So you have expectation of x1 plus expectation of x2 plus so on expectation of xn. So that would be, what is expectation of x1? That is mu square, sorry, mu, not mu square. And then what is the expectation of x2? That is mu, because I told you here. And then so on, mu. How many times? 30 times. This is 30, right? 1 by 30. So that would be 1 by 30 into 30 times mu. That would be mu, right? So expectation of x bar is going to be mu. So that means if the original population is normally distributed, then the x bar will have the same mean mu which the normal population had, right? Okay, and then we also have something called, okay, let me first calculate the mean and variance, and then we'll tell you that. And now let us calculate the variance of x bar. So that would be variance of x1 plus x2 plus so on xn divided by n, right? You want to take it 30, or n can be in general. Now do you remember this result, that if you have two random variables, then the variance is related as this: a square into variance of x plus b square into variance of y, okay, if x and y are independent. If they are not, then we have a covariance term also. Here all these are independent samples, right? So because here the samples are independent, so use this result. So 1 by a is 1 by n square sigma square x1 plus 1 by n square sigma square x2 and so on 1 by n square sigma square xn. Now these sigma square x1, all of them are sigma square because they are from the normal population with the variance sigma square. So this is sigma square, this is sigma square, this is sigma square. So this is 1 by n square, n times sigma square. So that is 1 by n sigma square. That is your sigma x bar square. So that means sigma, the standard deviation would be 1 by square root of n sigma. So right, so we saw that x bar has mean equal to mu, which was the population mean, and standard deviation equal to sigma over square root of n, where sigma was population standard deviation, right? And then we also have a property which is called reproductive property for normal distribution. Okay, so let me write down. So because the aim of this course right now is just to give you a glimpse, so I'll not go into the proofs. So we have something called reproductive property of normal distribution, which says, which is actually very easy to think about. Normal distribution, which says if x1, x2, xn are independent normal random variables, then x1 plus x2 plus so on xn divided by n is also a normal random variable. So what do we got from all of the discussion here? We get that x bar, which is x1 plus x2 plus so on xn divided by n. Okay, so this is nothing but sampling distribution of mean. Distribution of mean is normally distributed. So let me write like this: if the original population is normally distributed with mean equal to mu and variance is equal to sigma square, then this particular fellow here, which is nothing but the sampling distribution of mean, is also normally distributed, with mean equal to the same mean mu but standard deviation would be changed sigma by, it would be sigma by square root of n. The original standard deviation, here I have written variance, is sigma. Okay, so this is the result. This is very important result, that if your original population is normally distributed, then we expect that the sampling distribution of mean, which I told you in the last video, what is the sampling distribution of mean, is also normally distributed with the same mean, but the standard deviation changed, right? So now we will see that in the next video we are going to talk about a very important result, which is called central limit theorem, which says even if your original population is not normally distributed, right, then also you can expect this kind of behavior from the sampling distribution of mean. Okay, so thank you for watching this video. Have a nice day.